Hello everyone, Dr. Chen here. So we will discuss conservation of momentum and cognition in this lecture video. So we have learned the work and energy theorem. And the work and energy theorem give us conservation of energy. So we have one special case, which if the only force doing work to the system is conservative force, then we have mechanical energy conservation. If non-conservative force does work to the system, then the work done by non-conservative force equals to the change of mechanical energy of the system. So we have two versions of energy conservation theorem. And then we have an impulse momentum theorem, which is very similar to work energy theorem. Work energy theorem says the net work done on the system equals to the change of kinetic energy of the system. And we have learned the impulse momentum theorem. The impulse acting on the system equals to the change of momentum. Then are we going to have a conservation law based on impulse momentum theorem? And the answer is yes. And this is exactly the idea behind how we treat conditions of objects. And to study conditions, we have to distinguish internal forces and external forces. So we have two objects collide. And what is internal force? We have M1, M2, the force from M1 on M2, and the force from M2 on M1. We call those one internal forces. Forces that objects within the system exert on each other. Now, easy to understand, external forces are forces that acting by an agent which is outside of this system. So we have M1, M2. External force would be from an object which is not M1 and M2 acting on M1, M2. Now, why do we want to distinguish internal forces and external forces? Because internal forces are special. So we apply impulse momentum theorem to M1. So the force from M2 on M1 times delta T give us change of momentum of M1. The force acting on M2, so which is applied by M1. The impulse received by M2 equals change of momentum of M2. But there is a relation between force from 2 on 1 and the force from 1 on 2, right? Which is Newton's third law, if you can recall. So F21 and F12, they form action-reaction pair. So they always equal magnitude and opposite direction. And F12 times T equals negative F121 delta T. Because F21 and F12, they are always equal magnitude and opposite direction. And delta T is always the same for internal forces because of Newton's third law. If there is F21, then there is equal magnitude opposite direction F12. So we have from here, right? F12 equals negative F21, so we have the change of momentum of M1 and the change of momentum M2 are equal magnitude and opposite direction. So put all that together, we find out the momentum of M1 plus M2. So this is initial momentum of the system equals to the final momentum of the system. Momentum of M1 plus momentum of M2 after the collision. So we kind of will have a conserved quantity, which is momentum. Momentum is conserved. Let's recall what's the condition we used to arrive at the conclusion that the momentum before the condition and the momentum after the condition are equal. So we have proved that impulse from internal forces are zero, right? We proved forces from internal forces are zero, but we didn't consider impulse from external forces. So if we have external forces and external forces give us a non-zero impulse, the momentum of the system is going to change. However, if the impulse by external force is zero, then we have initial momentum of the system is going to be equal to the final momentum of the system. So here is a condition. Here is a condition of the system, the conservation of momentum. It has to be an isolated system, such that the average external force acting on the force is zero, or the external impulse is zero, then the momentum of the system is conserved. And this is how we use the conservation of momentum principle to solve the problem. Now look at this one. Ice skating. We have two skaters. One 54 kilogram, another one is 88 kilogram. And at the beginning, they are all at rest. And then they give each other a push. And we know the final velocity of this woman. We want to find out what's the velocity of the man. So is the momentum conserved in this question? Now, of course, if we haven't learned conservation of momentum, we might be attempting to try to solve it using Newton's second law and kinematic equations. However, it will be very, very challenging. If we want to apply Newton's second law, now the only thing we know is that at the beginning they're at rest, and then at the end we know the velocity of her. And the force between the man and the woman, we don't know. It's a changing force. It could be anything. So acceleration is not a constant. We don't even have a simple kinematic equation to solve this one. So it'll be very difficult. I would say it's possible, but it'll be very, very complicated mathematically if you want to solve it using Newton's law of motion. However, now conservation of momentum will turn this question into a very, very mathematically simple form, and we can solve. So we know that at the beginning, the momentum of the system at rest. So momentum of the system before the pushes is zero. So if we can find out the system, the external forces acting on the system is zero, then final momentum should also be zero because of momentum conservation. So we need to check out whether the external forces acting on the system is zero. So if we look at the man, the external force, we have normal force, we have mg, and then we have the internal force. But we don't need to worry about the internal force, right? So, and these two forces should add up to zero because there's no acceleration in y direction at all. So net force in y direction has to be zero. External force at zero for the man. Same thing for the woman. Normal force. Mg for the woman should also cancel out because there is no motion in y direction at all. Those are the Now, if we can ignore, of course, we have to ignore friction in this question, because it says friction is negligible. Okay, those are the only four external forces acting on the system, and they add up to 0. So momentum is conserved, which is good. So we can apply the principle of conservation of momentum to solve this question. And we know at the beginning momentum is 0. At the beginning, before they push each other, total momentum of the system is 0 because both the man and the woman are at rest. So final momentum should also be 0. This final momentum equals initial momentum equals 0. Now we know mass of the man, we know mass of the woman, and we know velocity of the woman. Okay, so the velocity of the woman is positive. Plug in all the number. Mass of the woman, mass of the man. Now we find the man is backing off, recoiled with a smaller speed, negative 1.5. The woman is moving with velocity 2.5 meter per second. So as we discussed, this problem is not easy if we want to solve it using Newton's law, but if we use conservation of momentum to solve it, it becomes a very simple algebra equation. So here is what we need to do to apply the principle of conservation of linear momentum. We need to decide what are the objects in the system, and then what are the internal forces and external forces. We need to verify whether the external forces add up to 0, so the system is isolated, so momentum is conserved. And then we set a conservation of momentum equation. Final momentum equals initial momentum, and then solve whatever variable the question is asking us. Now we apply conservation of momentum to conditions. Here we just want to clarify a few concepts in condition. And there are several different kinds of condition. We have inelastic condition. In inelastic condition, momentum is conserved, but kinetic energy is not. And then we have perfectly inelastic condition, which means momentum is conserved, kinetic energy is not conserved, and the two objects stick together after the condition. Two objects will have the same final velocity. We have elastic condition. In elastic condition, momentum is conserved. Kinetic energy is conserved too. So we have two conservation equations. Summarize, we have three different scenarios of condition. Well, perfectly inelastic condition is a special case of inelastic condition, of course. Elastic condition means momentum and kinetic energy are both conserved. In inelastic condition, momentum is conserved, kinetic energy is not. We have perfectly inelastic condition, which means momentum is conserved, kinetic energy is not conserved. Two objects will have same final velocity. Sometimes it's also called total inelastic condition. Now, for all condition, if we use the word condition, condition just means momentum is conserved. If we say the word condition, we should understand we should use conservation of momentum to solve the problem. Condition means momentum of the system is conserved. Perfectly inelastic condition means two objects stuck together have the same final velocity after they collide. So this is initial momentum of the system, and because M2 have same final velocity, this is the final momentum of the system. So it can be very easily solved. Final momentum of the two objects after the collision would be initial momentum divided by M1 plus M2. For elastic collision, we need to build two equations. Momentum conservation equation and kinetic energy conservation equation. And then we need to solve the unknown variable from those two. Now, mathematically, if we know the initial velocity of those two objects, so which means we have two equations, one unknown, two unknown. So we only have two unknown, we have two equations we can solve.